Good morning and welcome to Saying Is Online series. Today I am going to introduce the Laplace transform to you. You may be surprised to see this birthday cake. There is a reason to show this image to you. The great mathematician Pierre Simon Laplace was born on March 23, 1749 in France. Surprisingly, today is his birthday. So I'm very happy to share this video to you on this great day on which the famous mathematician and also his philosopher Simon Laplace was born. Agenda of the lesson: introduction to the concept of transform, projection into exponential kernel, intuitive definition of the Laplace transform, and the mathematical formalism underlying the transforms. First of all, I would like to explain what is a transform. A transform or transformation is the process of shifting objects, phase, or anything of interest from one domain to another temporarily. So for example, I will give you an analogy. Suppose we have a full bottle Bisleri water and we are going to put it in the refrigerator. After 1 hour or 30 minutes, we will got chilled form of water. What is really happening here is simply transform the liquid form into solid form, nothing else. It is simply a phase transition. When we take the bottle back and put on the dining table, it melts and it will return to the liquid state, our water state. Such processes are known as transform or transformation in mathematics. Actually, it is a two-way journey. That means if we apply transformation on some object, it will change its form and it is reversible. After some time we will get back it. That process is called inverse transform. Now we are going to introduce the concept of integral transform and integral kernel. An integral transform is a mathematical function that continuously sums up a function after projecting it into some kernel. For a better understanding, you just look into this expression. This is a very simple mathematical expression. It says that we multiply f of t into some k of st, then integrate with respect to t. Integration is actually continuous summation. So this word continuous sum is satisfied by this integral expression. When we integrate with respect to t and after putting the limit, suppose you have some limit here, after putting the limit the variable t will be disappeared. So this parameter s will be there, and that is why output of this integral is denoted by f of s, because after the integration the only parameter is s. That means the function f is transformed from the domain t into s. So f of s, here f of s is the transformed output, and this k of xt is called the kernel. K of st is called kernel because this integral is purely depending on nature of this f of t and k of st. There are various type of k of st we are using in mathematics. Today we are going to discuss a special type of kernel. That kernel is very important because Laplace transform is making use of such a nice kernel. So next idea is projection into exponential kernels. The result of projection of f of t is actually depends on both its property and also the nature of kernel. If the kernel and f of t have some cumulative properties, then there is a cumulative effect in that integration. There are exponential kernels with the growth and decay behavior. Usually if you use some exponential function, it is considered as an exponential kernel. If the power of that exponential function is positive, it is called an exponential growth kernel. If the power of that exponential function is negative, it is called an exponential decay kernel. For a better understanding, we simply revise the De Moivre's formula that we have discussed in our +2 classes. That is, e raised to I theta is equal to cos theta plus I sin theta. Because of the presence of this I, it is a complex number. So I denote it as some z. Z is a complex variable x plus iy. Bring it together, I can write x plus iy is equal to e raised to I theta. But e raised to I theta is cos theta plus I sin theta. Now the left hand side is a complex number. Right hand side is also another complex number. Two complex numbers are equal only when the real part and the imaginary parts are equal. So we simply equating these real and imaginary parts. So x equal to cos theta and y is equal to sin theta. I put it equation number 3 and equation number 4 respectively. Now just for fun, I simply squaring both sides and adding these two equations. I got x square plus y square equal to cos square theta plus sin square theta. But from the basic trigonometric identity, cos square theta plus sin square theta is equal to 1. That means we starting from this complex expression, we come to an algebraic expression x square plus y square equal to 1. But we know x square plus y square is equal to 1 is a unit circle. That means e raised to I theta represents a circle. Here it is unit circle. So whenever we multiply a function f of t into e raised to it, we simply project f of t into e raised to it. Then automatically f of t is just rotating counterclockwise direction, because here I put plus sign. Plus sign means it is in counterclockwise direction. If we have negative sign here, it is clockwise direction. That means when we multiply f of t by some e raised to it, then it is simply rotating f of t. Now we are going to interpret Laplacian kernel in the light of this result. For simplicity, I consider e raised to minus st, a kernel e raised to minus st. That is, k of st is equal to e raised to minus st. Then this s is sigma plus I omega. So sigma is the real part, omega is the imaginary part. That means the power contains a complex number, sigma plus I omega. Now we simply multiply this e raised to minus st by f of t. F of t is projected into e raised to minus st equal to f of t into e raised to minus of, instead of s I put sigma plus I omega. Then using the law of exponents, I can rewrite this e raised to minus of omega plus I omega t as f of t into e raised to sigma t, e raised to minus sigma t into e raised to minus I omega t. Now consider this box set part. It means we project f of t into e raised to minus sigma t. E raised to minus sigma t represents an exponential decay, or simply f of t is decayed exponentially. This box set expression means f of t is decayed exponentially. Definitely the sigma has a role in this decay. Now we multiply this box set expression into e raised to minus I omega t. In the previous slide, we know e raised to I omega t is actually the part of circulation. When we multiply this function into e raised to minus I omega t, we rotate this box set expression in clockwise direction. Minus means clockwise. Or simply f of t into e raised to minus st decayed this function f of t exponentially and rotate by this angle omega. So f of t into e raised to minus st is nothing but it is an exponential decay followed by a circulation or rotation. So these parameters sigma and omega are considered as the hour and minute handle for the transformed clock to S-spline. It's an analogy. As we know, we measure the time using the hour hand and minutes hand for simplicity. Suppose the time is 10:45. That means the hour hand points to somewhere after 10 o'clock, after the digit value 10, and the minutes hand points to 45. That means the hour hand represents the magnitude and this minutes hand represents the completed rotation, how much it completed the next rotation. And similarly, the sigma denotes the measure of magnitude, exponential magnitude, and omega means the exponential rotation. It is like a fictitious twister game, the dynamically collapsing shafts and spindle. We all are familiar with amusement parks. There is a wonderful game Twister. This twister has a shaft, and at the end of the shaft there is a seat. Actually, we are sitting in that seat. When the twister game starts, the shaft will rotate horizontally, and at that time our seat will be fixed. After some time, this shaft will rotate and it changes direction, and also our seat start to rotate, and it is a magnifying effect on the people who are sitting in the seat. Suppose in this twister game the shaft is dynamically collapsing. Initially, suppose it has 10-meter length. After some time, this length automatically reduces, and the shaft will come down, and also the spindle rotates. The same effect will experienced when we apply this Laplacian kernel of a function. Okay, now we look into an intuitive picture. I have taken this image from a wonderful YouTube video that explained the Laplace transform intuitively with some wonderful visualization. Here, this particular spike with this bead represents f of t into e raised to minus sigma t. This one, f of t into e raised to minus sigma t. Then when we multiply it into e raised to minus I omega t, this will start rotates about this axis. So this totality gives the Laplace transform. Actually, this is the Laplace transform of that function at a particular time t1. This is the Laplace transform at a particular time t2. Like that. When we take whole together, that is the integration, whole together, we get the complete Laplace transform. So we simply multiply that function by an exponential function, that is actually leads to an exponential decay, then followed by a rotation. So we come to the formal definition of the Laplace transform. Formally, the Laplace transform of a piecewise continuous function f of t on a positive time domain is defined like this. It is an integral. This integral means the continuous summation over t from 0 to infinity. That means we take only positive time. We multiply f of t by e raised to minus st. That means we project f of t into e raised to minus st. Remember, s is the complex number sigma plus I omega t. So f of t is decayed exponentially and rotate, then we take the totality. The total is called the Laplace transform. When this s is equal to 0, automatically e raised to minus st becomes 1. E raised to 0 is 1. Then integral 0 to infinity f of t dt is simply area under the curve f of t in time domain. That is, the Laplace transform take the function f of t into frequency domain, this s domain, followed by an exponential decay over time. Then why we are using Laplace transform extensively in engineering? There are 4 important reasons I have listed. The first one is it is a magic tool in engineer's toolbox, because it has a wonderful effect on doing things in simplification, etc. In signal theory and also in communication theory, when we apply the Laplace transform of a signal, it will convert it to the frequency domain. In time domain, the analysis of signal is very difficult. In frequency domain, it is simply the analysis of zeros and poles in complex plane. That much simplicity we can experience when we apply Laplace transform on continuous signals or analog signals. The second point is it transformed complicated operations to simple one in frequency domain. It's a very important application, like the use of logarithm in previous years. We know that logarithm of a into b is equal to log a plus log b. That means logarithm of product is equal to sum of individual logarithms. So in original domain, we multiply a into b. In the log domain, we simply take the sum. So summation is very simple. That is why we are using logarithm in initial days. Now that position is replaced by scientific calculators. We don't want any logarithm anymore. But anyway, the complicated operations can be simplified with some tools. So Laplace transform is such a tool, because suppose we are going to differentiate a function, that means we have a derivative. We need the derivative. When we take the Laplace transform of derivative is simply multiplication by this s. So differentiation in time domain becomes a multiplication by s in frequency domain or s domain. Similarly, Laplace transform of integral becomes a division by s in frequency domain. That means in order to integrate a function in time domain, in frequency domain we simply divide that transform by s. That's all. That much wonderful properties are experienced when we are using Laplace transform on functions in time domain. The fourth property is mathematically very much important. It is the mother of modern axiomatic probability theory. Actually, expectation is the base of probability theory. Expectation is calculated as an integral x into its probability mass function. Actually, this probability mass function is a kernel which satisfies some normalization property and non-negativity property. And so the Laplace transform is the base of the modern probability theory. In all these ways, we cannot exempt this Laplace transform from our study. And one more thing, this Laplace transform can be used to solve ordinary differential equations of any order. And therefore, in the previous modules we have discussed how to solve differential equation, how to solve ordinary differential equation, etc. Laplace transform is a wonderful tool to solve more complicated differential equations without much effort. In all these views, Laplace transform is very important, and it is very nice to see the visualizations, and it's a wonder even before that much years back how these scientists can visualize this transform and the utility of this transform. It is an amazing thing. Anyway, the Laplace transform is a wonderful thing. Now I am going to show you a funny image that explained a simple Laplace transform. And look into this figure. Actually, an employee, he simply pull up a carpet and sweep all the errors and put it into that gap, in the gap that created by lifting this carpet. Now look this shape of the carpet. This carpet has a particular shape, and it is shown in this orange color. It is actually Laplace transform of 1. The Laplace transform of 1 is actually 1 by s. The graph of 1 by s gives this structure. So when we pull up a carpet, it creates a Laplace transform, that is Laplace transform of 1. And so we can use this Laplace transform to create wonderful animations without much effort. So this is all about an initial view of Laplace transform and interesting features. And actually the Laplace transform is not invented by Laplace himself. It's actually formally introduced by Leonhard Euler, the great mathematician. He simply reformulated in a different way. So Euler is considered to be the inventor of the crude form of Laplace transform. Okay, thank you very much.